Okay, so we just discussed the graphs for sine and cosine. And so now the next interesting thing to discuss is wave motion and how waves actually arise from sine and cosine functions. So as you can tell from the graph, it already looks sort of like a wave. But really, what is a wave and how does sine and cosine express it? Because clearly there's characteristics of a wave that we want to be able to capture. So to start off is, well, sine and cosine functions were just graphed based on this angle that we rotated around in a unit circle. But waves are actually something that's based in time. So we have to convert something in the circle to time in order to actually get a wave, right? Because, let's just think about it. Just on the computer, to be able to hear my voice, there is some kind of magnetic speaker where there may be something attached onto a magnetic coil that causes the speaker to go up and down to generate a sound wave, by the speaker coming, bulging outward and bulging in and repeating it back and forth. So it creates some kind of a wave. So if you just graph the position of this sort of oscillating thing over time, I'll just make up something reasonable. It may just look like some kind of thing that repeats, right? And then this gives a wave at a specific frequency. So before I get into the details, let's just define some terminology. One is about, on the speaker, of when the speaker, goes back and forth and oscillates, and then you hear the noise, that gets generated from it. There's a few things that's characteristic. One is a pitch, right, of the actual sound. So the pitch of the sound is, in mathematical terms, is called the frequency. And the frequency means how many times per second you actually get through this. So actually, before defining pitch, let's define a period. So a period is the basic length of a cycle that repeats. So you can see here that after this cycle, it will repeat again and again and again. So this is the basic unit of repeat. So the length of time for this one cycle of repetition. So I started it here arbitrarily. I could have also started it here and here, and I could say this part repeats, right? But the length is going to be exactly the same for periodic things. So this length of time for a curve to actually repeat is called the period. So let's say here is that it's actually going to be 10 seconds or something, or actually 10 seconds is quite long. So let's say 1 millisecond, right? So that means in 1 second we're going to get 1,000 of these up-down pairs. So this is called the period, and normally in mathematical notation it's denoted by t. And why is it t? Because it's the length of time, and it's sort of a fixed length of time. So this is called the period of a wave. Now what about the frequency? Well, the frequency is about how many of these things occur per second. So here the period was 1 millisecond, right? And the frequency is going to be essentially how much time it takes to actually get this period. So let's just say it's 1 divided by t. So this means it's here it would be 1 second divided by 1 millisecond, and or 1 divided by 1 millisecond. So how many times per second does it occur? And that gives us 1,000, these sort of repeated patterns per second. And so instead of just saying 1,000 somethings per second, 1,000 these things per second, mathematicians came up with a word for how many of these repeated units occur per second, and they call it hertz. So 1,000 hertz means 1,000 of these up-down patterns occur per second, right? So 1 second goes like this 1,000 times. So that is the frequency, and how fast it actually, how many times per second this occurs actually determines our pitch. So the longer it is, the lower the pitch will be, and the higher, or the closer together these things are, the higher the pitch will actually be. Now there's another notion is about, it's not just the pitch of the sound. There's also, two people can sing in exactly the same note, but they can sing at different loudness levels. And so in mathematical terms, that is called the amplitude of the wave. And the amplitude of the wave is defined as the distance. So the wave always goes up and down, up and down. So there's always going to be some like total distance from the top of the wave to the bottom of the wave. But because the wave is symmetric of how much it goes up and how much it goes down, like for a speaker, how much it actually bulges up and how much it actually goes down, like a spring, is actually the same. So the amplitude is defined as the distance from the equilibrium position, which means if you have no sound and the speaker was off, to the maximum position when the speaker is like bulged out the maximum or something like that. So this distance from here to here is going to be called the amplitude. So amplitude. And of course, this is going to determine how loud the wave is going to be. So these are the basic, okay, so one other thing is, this high point in the wave where it gets up to the top, so this is related now to more water than actually acoustics. This is called the peak. And then the most bottom part is going to be called the trough of the wave. So these are just terminology, and then this middle point here is going to be called the equilibrium position. That means that if it wasn't vibrating at all, this is the position that it would actually stay in. And when it's vibrating, then we go up and down, up and down, up and down to generate the sounds for the speaker. So this is the basics of wave motion. And so after this, I'll talk about the relation between the trigonometric functions sine and cosine and wave motion. And as we'll see, is that sine and cosine are actually the most natural representations of wave motion.